Let me show you how to do this question today. This question is from the HAC 1996, question 8. It's the last question in the paper, so it's going to be a little bit harder. It's about relation between the complex number and the trigonometry this time. As my last video, I showed you the question was about relation between the complex number and the polynomial equations. And my other video also show you about the relation between the complex number and the exponential functions, which is Euler formulas. So complex number has a lot of relation between the other functions and other stuff, like sometimes it also can be treated as a vectors, can do lots of vector proofs by using complex numbers. So this question today is about relation about complex number and the trigonometry. So I'm going to show you how. So let's start the questions. Question 1. Let W is equals to cis 2 pi r 9. Cis means cos plus I sine. And we're going to show WK is a solution of set 9 minus 1 equal to 0. So usually how do we show something is a solution of the equation? We sub in that something into the equation, see if it's satisfied. So I'm going to sub WK into the equation. So left hand side of the equation is z12 9 minus 1. And I'm going to sub in WK inside. WK to the power of 9 minus 1. And the WK to the power of 9 is same as W9K minus 1. It's same as W9 to the power of K minus 1. And W is cis 2 pi r 9. So to the power of 9 and then to the power of K minus 1. I'm going to using De Moivre theorem. Cis 2 pi r 9 to the power of 9 is same as cis 2 pi. Then to the power of K minus 1, which is 1 to the power of K minus 1, give you 0, which equal to right hand side. That's it, we proved. We proved WK is a solution of the equation set to power 9 minus 1 equal to 0. How we proved? We actually used the De Moivre theorem. We proved that W to the power of 9 is equals to 1. And by using this solution here, now we can do the second questions. So let's have a look what's the second questions. So prove W plus W squared plus W cubed all the way to W8 equal -1. Since we proved WK, case any integer would be the solution of the equation set 9 minus 1 equal to 0. So as I can see, all these numbers, W squared, W3, W4, all the way to W8, it's going to be a solution of set to power 9 minus 1 equal to 0. And also including set W to the power of 9. So this 9 root would be, the sum would be equals to negative B on A. And the B is equal to 0 in these equations. So sum of the roots is going to be equal to 0. I'm going to using this result to prove that. So the roots of z to the power of 9 minus 1 equal to 0 are, I'm going to write it down. So it could be W squared, because we proved WK is also the roots, right? So all this is WK. K equal to 1, 2, 3, 4, 5, 6, 7, 8, 9. So these are the 9 roots. And the sum of these roots, I'm going to adding them. It's going to be negative B on A, where the B is equal to 0. So they're going to be equal to 0. And we know W to the power of 9 is also equals to 1, as we proved previously here. So I'm going to change in that into 1 here. So then I'm going to have all of these I just copy all this down, W5, W6, W7, W8, plus 1 equal to 0. And I can move the 1 to the other side, and I'm going to just quick write all these down. W5, 6, 7, and 8 equal to negative 1. Proved. As you can see, the question asks you prove equal to negative 1. Okay, so now the last sentence you can see is a purely trigonometry. This is how we turning complex numbers into trigonometry. So you can see all the W is a cis. But now we need to prove in cos. So how do we turn in cis into cos? So we know our one important result. I'm going to write it in here. I'll write this one in here. So we know cis theta plus cis negative theta is equal to 2 cos theta, right? So that's one solution, or in general we can even put a cis n theta plus cis negative n theta would be equals to 2 cos n theta. So this is the results we're going to use in here. Because we have all the cis right now, W is a cis, and I'm going to change the cos. So if they do have this conjugate pair in the questions, then we can say we have the cos. So let's see if we have conjugate pairs. So now we have W plus W8. Let's see this first pair here. Are they conjugate pairs? Let's check. So W is equal to cis 2 pi on 9. And W8 is equals to cis 16 pi on 9. And we know 16 pi on 9 is same as cis negative 2 pi on 9, right? So they are actually are conjugate pairs. So these two are conjugate pairs. So similarly, we can say the other ones like these greens, they also conjugate pairs. The yellows are conjugate pairs. And the last pair, I'm going to the red. So they also conjugate pairs. So I'm going to plus them, and when you plus them, become 2 cos. So I change my question now into 2 cos 2 pi on 9 plus 2 cos the green pair now. So it's 4 pi on 9. And the next one is a yellow pair now. So 2 cos 6 pi on 9. And the last one is the red pair, will be 2 cos 8 pi on 9. So that will give me equal to negative 1. So that's already changing the trigonometry now, because before was the cis with complex number, now become trigonometry. So in the trigonometry here, we are very close. So we have all the cos, and we have 2 everywhere. So I'm going to first tidy them up, move the 2 onto the other side. So give me 2 cos 2 pi on 9, cos 4 pi on 9, cos 6 pi on 9, cos 8 pi on 9, equals to negative half. Okay, let's go back to have the questions. Question asks you proving cos pi on 9 time cos 2 pi on 9 time cos 4 pi on 9. But right now we have cos 2 pi on 9 plus, we have all the plus. The question asks prove time. But we have formula, we can change the sum into product. So this is the formula I'm going to using. So first one, I'm going to bring these two sum into a product, and then bring these two into another product. So let's do this. So we're changing that. So cos 2 pi on 9 plus cos 4 pi on 9 is equals to 2 cos 2 pi on 9 plus 4 pi on 9 all over 2 and the cos 2 pi on 9 minus 4 pi on 9 all over 2. So this one give me the blue. I change the sum into product. And then I'm going to do the green pairs. So the green pair become plus 2 cos 6 pi on 9 plus 8 pi on 9 all over 2 and the cos 6 pi on 9 minus 8 pi on 9 all over 2. So this is the green pair. So that's supposed to be equals to negative half. Okay. The 2 we can move to other side and then we tidy up the rest of the cos. So first cos we're going to have 3 pi on 9 times cos negative pi on 9, but cos is even function, so it becomes same as positive pi on 9. And the next one, so become cos 6 plus 8, 14 on 2, 7 pi on 9. And the cos negative pi on 9. Cos negative pi on 9 is the same as cos pi on 9 since cos is even functions. So that equals to, don't forget 2 divided to other side become negative a quarter. Okay, we're so close. So we both have cos pi on 9. So we can take it outside. And then leave me with cos 3 pi on 9 plus cos 7 pi on 9. And then equals to negative 1 on 4. Okay, again, I have the last pair of the sum. I'm going to change that product again. So leave the cos pi on 9. And this one become 2 cos 3 pi on 9 plus 7 pi on 9 on 2. And the cos 3 pi on 9 minus 7 pi on 9 all on 2 equals to negative quarter. Right, so let's tidy up. So cos pi on 9 stay here, and the 2 I'm going to divide to the other side. So then this one is cos 5 pi on 9. And the other one is cos negative 2 pi on 9. But cos negative 2 pi on 9 is the same as cos 2 pi on 9 because cos is even function again. And don't forget the 2 divided to other side become negative 8, 1 over 8. So we're so close. We have pi on 9, 5 pi on 9, 2 pi on 9. And the question is, let's check the questions. Pi on 9, 2 pi on 9, 4 pi on 9. So we have 5 pi on 9 instead of 4 pi on 9. But we know the cos 5 pi on 9 is equal to negative cos 4 pi on 9. So I'm going to change in that. Cos pi on 9, cos 2 pi on 9, and the negative cos 4 pi on 9 equals to negative 1 over 8. And then I divide the negative to the other side. So become cos pi on 9, cos 2 pi on 9, and the cos positive plus 4 pi on 9. That equals to positive 1 over 8. Then we're done.